I just wanted to ask, could you elaborate on your last comment about higher H-bar correction?
Can you speak louder?
Yeah. Could you elaborate on your last comment on this higher H-bar correction a little bit more?
On what?
Higher H-bar correction.
Okay,
your comment. Yeah.
So yeah, what I was saying is that. Okay, what we want to get is something like that. And so what you've seen in the array curve case is that you got an ansatz, some kind of WKB ansatz, which was that you were looking for a solution of this form. Times a constant times 1 plus sum over h from 0 to infinity, h bar to the power h fh of x.
H bar equals the x bar.
Yeah, thank you. Now, if you plug that into this equation, so this guess for the solution, so it's called the WKB form, and you look at the h bar expansion of the equation you get, the leading order, so the leading order in h bar, will be the fact that y squared minus q of x should be vanishing. So it fixes y. This is basically what I derived for any curves there. So the spectral curve expression is basically this leading order that I would be looking for. So it gives me a bit of an idea of the equation I would get, but then I've got some subleading order in h bar. And they give me constraint on the fh and kappa here, okay? Order by order. So I will get an infinite order of equation, which will fix the kappa and fh starting from this. Now, what I will do now is basically go bottom up. I will build this infinite order of equation and say, okay, we can resum them together in order to get an equation of this type, okay? And what I like about the expression I got for the spectral curve is that I've got an expression with only the t's and action of d over dt on some omega 0, 0. So you would say, okay, if I would have to go to higher order in h bar, maybe I can replace omega 0, 0 by omega h0. So it's a very naive guess, but it's not far from what is going on.
What is
K? It's a constant in h bar, which you have to fix. And so it will be given by the second equation. Okay. Is there any other question before I go? Okay, so the idea is that I want to build this psi x of x and h bar. So let's do it. For this so this is what I will call the wave function. And here I will be perturbative. So in order to do that, I will have to introduce a few notation. First of all, I consider omega 0, 1. So it's a 1 form. And out of it, I will build a function just by integrating it from sigma of z to z, and I will call that f01 of z. Okay? Then I will try to do the same thing for f02 of z1, z2. I would like to take omega 02, integrate it from sigma of z1 to z1, sigma of z2 to z2, with a factor 1 over 4 for each of them. But here there is something I don't like, is that when z1 goes to z2, omega 02 has a pole, and so it's not well defined here. So there are many ways to fix this, but in this case, I will just remove some singular parts by removing 1/2 of log of x of z1 minus x of z2. exercise, you can show that when Z1 goes to 0, Z2, this is regular. So should I write bigger, Martha?
Yes.
Okay. So this is for the first two objects. And now I would like to define FHN of Z1 to the n in the same way. So I take omega hn, it's an n form, and I integrate it n times, so each variable from sigma of Z1 to Z1 for the first one, up to sigma of Zn to Zn, and I remove a symmetry by dividing each integral by 1/2, multiplying by 1/2. So out of that, for each a and n, I did build some primitive, let's say, of omega hn. Nobody is complaining? Okay. Let me complain for you. Here I'm being very sloppy. I mean, this integral, you've got to be very precise when you define them. Actually, what you should consider are function of path on your spectral curve going from sigma of Z1 to Z1 and from sigma of Zn to Zn. So I will not enter these details here. We just pick one on sigma minus the poles and a priori minus the branch points. But actually, when we go around branch point, because of a property of the omega hn, not much changes because the omega hn do not have any residue at the branch point. So this is one of the things you will do in the exercise. Yeah?
What if you go around the big cycle?
So if you go around the big cycle, you've got some issue as well. So you've got to cut, for example, I mean, there are many ways to do it, but cut a fundamental domain, for example, on your spectral curve, remove the poles, and then you choose a path of integration for your sigma, going from sigma of Zn to Zn. This is one way of defining the FHN. It's not the only way for building the psi. Actually, Bertrand worked a lot on choosing some kind of arbitrary divisor for integrating, and it provides different solutions to the differential equation we will get. I mean, different differential equations themselves. They will be a bit different depending on the integration path you take. But so for today, I just choose that, and I will make use of the symmetry of the spectral curve here, the fact that I've got an hyperelliptic curve. Okay. So now that I've defined this f, I will define some additional objects, which are, no, they are not function of point on the spectral curve, but they are function of point on the base curve. So I remind you that we had a double cover. So in our case, it had this form. And the f, they depend on points here on the spectral curve. And what I will build is something which depends on a point in P1 on the base curve. And for doing that, I just take F01. And I evaluate it at Z of x, where I make an arbitrary choice. So let's say before we had this plus minus labeling. If I've got x here, let's say that Z of x is the point in the plus sheet of the cover, which is in the fiber above x. Okay? And then, yeah. And depending, I will build two such functions, labeled by plus and minus. Will differ by a sign. And they just correspond to the different choices of labeling of the sheets. Okay? I do the same thing for S0 of x, plus and minus. So I will take F02, and I take Z of x, divided by 1/2. So what do? I take my F02, which is regular when Z1 goes to Z2. So I evaluate both of them to be at the point in the first sheet of the cover above X, okay? And I divide by 1/2. I multiply by 1/2. And for...
So is there a sign in this formula at all?
No.
So these two functions are the same?
So you see the sign, it amounts for exchanging Z and sigma of Z, Z of X and sigma of Z of X. So which I change the integration here. So it changes the sign. Here you've got two integration. So you change sign twice. And so for k greater or equal to 1, you get that hk, and we define it in this way, of x. You do exactly the same thing. Yeah, I will write it below. So I take omega hn, sorry. I take fhn, evaluated at c of x, so it has n variable. All of them, I put them to be at c of x. Multiply by -1 to the power n, divide by n factorial. And now what I do is that I sum over h positive n greater or equal to 1, such that 2h minus 2 plus n is equal to k. So this amounts basically for the power of h bar that you should have by looking at the omega hn weighted by h bar to the power 2h minus 2 plus n. So that's the definition. And now it means that I can build some...
Wait, and now in this case, the -1 is only for the minus? Or
Sorry?
so this -1 is...
So you take fhn.
S plus and S minus, and now there is...
Yeah.
So, thanks.
Sorry. So yeah, so as we've seen here, it's exactly the same thing here. This plus and minus, it just amounts for choosing different labeling, if you wish, here.
2k minus 2 plus n positive, right?
Sorry?
2k minus 2 plus n.
2h minus 2 plus n.
Greater or equal than 0.
Yeah.
Well, it is greater than 1. K is greater than...
What's the issue here?
It's not an equality.
What is not an equality? Such that you have that.
Ah,
So you fix...
That's a summation.
Okay, so yeah, it's in the summation, sorry. So you want to build sk, so you fix k greater or equal to 1. This is fixed. Now, you take all the fhn, and you sum over h greater than 0, n greater than 1, such that you have that. So the idea, let me just write it here. Usually, omega hn is weighted by h bar to the power 2h minus 2 plus n. And here, we just want to collect all of them, all the omega hn, which give us h bar to the power k contribution. OK? So now out of that, I can build two perturbative wave functions, which we would love to be a solution to a differential equation, but it will not be the case in general. So what do? Do as usual. Now you sum over k from -1 to infinity. H bar to the power k is k plus minus of x. And you just exponentiate that. So if you look at it, the leading order is exponential h bar to the power minus 1 s minus 1 of x, which is f01, which is the primitive of omega 01, which is exactly the answers I was taking before. And now I'm saying, okay, maybe I know the correction I need to do in the h bar expansion. So maybe I can fix the kappa and all the other order by using this formula. This is the formula which was working for the array case. So let's try to prove that it's working here. Before going there, I will define as well the perturbative partition function. So you see I excluded the n equals to 0 from this. Yeah, question?
What will happen if you change the interval of the integral not from the involuted Zn but from infinity?
Here?
Yeah.
So first, it depends on the curve. And second, you will be able to get a differential equation which might not be the one I get here. A bit different. So there are many choices you can make.
Sorry. Are they related? Will there?
Yes, they are related. So,
Okay.
so for example, in the most recent paper we did with Olivier, Elba, and Bertrand, this is the kind of normalization we've taken.
Okay.
Okay?
So, specifically here, you choose it because.
Because we've got an hyperelliptic curve, and we can use the symmetry of the hyperelliptic curve to make the computation easier.
I see. Okay.
Because depending on the integration path you take, the computation might be much more complicated. You can write down an equation, which Bertrand derived, for a very general choice. But in order to reduce it to an equation you can use in order to produce a differential equation, you've got to be very careful, and it might be very technical to derive it depending on the integration path you take. Yeah.
If you write perturbative wave function, this refers to the fact that you assume that h bar is a formal parameter?
No.
Or
No, it refers to the fact that if I take the log of psi, it's a series in h bar.
but a formal power series?
But it's a formal power series, yeah. So whatever happens, everything I do is completely formal in h bar.
Okay.
But you will see in Olivier's part that this is actually a very simple object compared to what you need to introduce.
Thanks.
No more question? Okay, so let's introduce as well. So here, yeah, sorry. I just want to make clear that this depends on x and h bar. We can as well build some z of h bar, but just taking the n equals to 0 contribution, meaning that you don't have any variables, so you don't have to integrate anything. You just take the sum for h ranging from 0 to infinity, h bar to the power 2h minus 2 omega h 0. So here I make the choice to separate the n equals to 0 from the n different from 0. You could also put them together in the definition of the wave function. It's just a different way to present it. And for people interested in integrable system, we hope that this would be the isomonodic tau function associated to the differential equation we will build. Okay. Now, the most important point. So I have up to 55, so 25 minutes. Okay. Okay.
Sorry.
Yeah.
Do you have the relation between like the psi function and the z function, like the known relation between the wave function and the partition function in integrable system? I mean, like.
No.
Okay.
Okay, I think
With the shift
expressing this,
Yeah,
this in
sign
terms of integral of
yes.
not yet.
Okay.
I mean, so it's for next week for the project session, if you will.
Okay. Thanks.
But anyway, I'm sure it doesn't work at this level. It will work at the non-perturbative level, most probably. Okay, now we would love it to be a solution to a differential equation in X. But it will not be the case. What we will show is that it's a solution to a partial differential equation. So it will include derivative with respect to X, but also derivative with respect to the times, the t's. So let's derive it. So for this, I will have to introduce a few notation. So first of all, let's define k of z1z as you take omega 02. So you've got this, you've seen this already today. You integrate it from sigma of z to z. That's what we usually call the recursion kernel. So that's the factor which appears in the topological recursion formula. And I will introduce something which is very much related to the topological recursion formula, but after doing this kind of integration. From what I could hear, from what Bertrand told me, he introduced some function R of Gn. I'm introducing some R as well. It is pretty much related to what he introduced, but it's not exactly the same. So please don't be confused. So I introduce Rhn of z1 to zn as being given by this. So you take f h minus 1 n plus 1 of u1, u2, z2 up to zn plus, so I will tell you what this means, sum of a stable, okay, stable element, h1 plus h2 is equal to h, a, b being a partition of z2 to zn, f h1 cardinal of a plus 1 of u1 a, f h2 cardinal of b plus 1 u2 b. So I get this big thing which I will tell you more about it. So it's a function of u1, u2. You take the exterior derivative with u1 and u2. And you evaluate it at u1 is equal to z1, u2 is equal to sigma of z1. So I'm not done, but I just want to tell you what this sum over h1, h2, a, and b over stable cases means. You remember for the topological recursion formula, which is there, I was removing the omega 01. The omega 01 cases here. What I'm doing here is that I remove the case where I've got 01 here or there, but I also remove the 02 as well. Okay? So what I need is that h1 a plus 1 doesn't give me either 01 or 02, and the same for h2 b plus 1. Okay? But since I remove them, I just want to put them back because I will need them, but they will play a very particular role. So I sum over j ranging from 1 to n, 1 over 2. So first, I put what would be the omega 02 contribution here with u1 equal to z1 times d sigma of z1 f h n minus 1 sigma of Z1. Yeah, will not have space. Sigma of Zj omega 0, 2 of Z1 dot times d sigma of Z1 Fh n minus 1 sigma of Z1 Z, and here I will just tell you what this notation means. And I'm sure Marta cannot read. So you just take what is here, and you consider the case where you would have 0, 2 here. So you get omega 0, 2, integrating just once because you take a derivative. And you take what should be left. It should be Fh n minus 1. But since A here is chosen to be Zj, you've got to remove Zj from the set Z2 to Zn. So Fh n minus 1 has n minus 1 variable. The first one is sigma of Z1. And what is remaining is Z2 up to Zn, where I remove Zj. Is it clear? And so I do the same thing when I change the role of Z1 and sigma of Z1. Yeah. This one? Yeah, so maybe I will. Can I write it on the other board? Are they asking the same thing? Okay, so the following is here. So it's the sum from j going from 1 to n, integral from sigma of Zj to Zj, omega 0, 2 of Z1 times d sigma of Z1 Fh n minus 1 sigma of Z1. And here, let me write it in this way. You take the set Z2 to Zn, but we'll remove the Zj, okay? And there is a 1 over 2, and there is one last term, which is sum from j equals 1 to n, 1 over 2, and it is exactly the same formula. Where you exchange Z1 and sigma of Z1. Okay, so what did I do? I wanted to have kind of the integration of the topological this part of the topological equation formula with respect to Z2 up to Zn. But in order to show how it is, I separated the terms where I had omega 0, 2 and the term where it was not. Okay? Now, yeah. Why did I do that? Because I basically want to write down a Cauchy formula for the topological equation. So the topological equation, you see, it's just a sum of residues at branch point of some differential in Z. Now, if I look at this differential in Z, I can look at all the poles it can have. It can have poles at the branch point because the omega here in general have poles at the branch point. But it could have also poles when Z goes to Z1, for example, here, because you've got a simple pole, or when Z goes to one of the Zj, when I've got omega 0, 2 here, which are the terms which are here. So what I could try to do is to say, okay, so what if I would take the sum over all poles of the residue at all the poles of this formula? I can move my integration contour, and if the curve doesn't have genus 0, I get something which is an integral along the boundary of a fundamental domain. And this is what I will write down now. If it would be a genus 0 curve, I would have that the sum of the residue would be vanishing. But in general, it is not the case. And this is the big complication of the non-vanishing genus case. So let's write down the formula. I just take the fundamental domain.
That's tiny.
Is it better?
Yes.
Yeah. So for example, I obtain it by cutting my curve along the A and B cycle I use for omega 0, 2. So if it would be genus 1, as the case I was considering, I would cut it along this basis of A and B cycle. What I get is a fundamental domain of this type. Okay? I guess you've all seen that quite a lot of time. And now what I compute is, is the following thing. I take 1 over 2 by I. I integrate along the boundary of my fundamental domain D. And I integrate K of Z1 Z, so it's for Z integrated R H N of Z Z2 up to the n. RHN is what I define there. First variable is the one I integrate, and I go from Z2 to the n. So it is equal to what? It is equal to a sum of residues. So I will get just residues at all the poles of the form that I am integrating here in Z. And these poles, we can check it. Yeah. Yeah. What are they? So as I said, there are poles at the branch point. So there is a sum over P being a branch point, plus sum over all the i's. Of the same thing. Okay, so just simple, just moving the integration contour. So for the moment, I leave this side without touching it, and now I look at the right-hand side, and I want to compute it. If you look at the sum of a branch point of residue at the branch point of K, Z1, Z, R, H, N, you will see that it's very similar to the topological equation formula that we had before. And it will just give you a simple answer obtained just by integrating Z2 to Zn in the topological equation formula. So this will be just equal to the, so it's TZ1 FHN of Z1, Z2 to Zn. So in order to get it, you just take your recursion formula, you integrate Z2 up to Zn along the same path of integration I choose here for the definition of my f, and you get this formula here. So that's a very simple exercise. So this is known. So we just have to evaluate these guys. So just take the residue when Z goes to Zj. But they are not very complicated, you see. Where do they come from? You will not have anything coming from here. You have poles coming from K. So when Z goes to Z1, you have a simple pole here, which you can evaluate. So it will just give you the value of this when Z equals to Z1 times the value of this at Z1, which is what I did right down here. And now we just have to compute as well the residue when Z goes to Zj for j different from 1. You don't have anything coming from here, but you've got something coming from there, just from the omega 0 2 terms. Okay? So I will skip the computation because it will take just a bit too long. But what you need to use in order to simplify the computation is that omega h n plus 1 of z z1 to the n plus omega h n plus 1 of sigma of z z1 up to the n is vanishing except for omega 0 2. So except for h equals to 0 and n equals to 1, in which case it's equal to dx of z, dx of z1 divided by x of z minus x of z1 squared. So that's a good exercise to prove this. This is true for any hyperelliptic curve. It is just a generalization of the fact that y of z plus y of sigma of z is equal to 0. So you change the sign of y when you go from one sheet to the other. So using that and just computing residue at point where you have simple poles, what you obtain at the end of the day is the following equation. So you have that this guy 2 pi is equal to, and here there is a big formula. It's dz1 fhn of z1 cn plus sum over j from 2 to n integral from sigma of cj omega 0 2 of z1 times dz1 fhn minus 1 of z1, you remove zj to the n, and you divide by omega 2 times omega 0 1 of z1, minus something very similar when you exchange the role of z1 and zj. So it goes from z2 to the n, divided by 2 times omega 0 1 of zj, plus, and one last term, 1 over 2 times omega 0 1 of z1, du1 du2, f h h minus 1 and plus 1 of u1, u2, c2 up to the n, plus sum of a stable term as before, and it's exactly the same sum. u1a fh2 b plus 1 U2B, where you evaluate it at U1 is equal to U2 is equal to C1. So this is just the result of computing the residue. And now I'm almost there. I guess this looks very similar to the computation Bertrand has done in the array case on the right-hand side. But now we've got this part which is not there if you've got a genus zero curve. And because we've got an hyperelliptic curve, what we can show is the following thing. If you look at it, and you can do that as an exercise, as a function of Z1, you can use Riemann bilinear identity in order to prove that it is a holomorphic form in Z1. And there is a nice formula, which is that if omega is holomorphic, so if it's a holomorphic one form, on an hyperelliptic curve, you have that 2 times y of Z1, omega of Z1, divided by dx of Z1 is equal to the sum over the poles, which are the alphas and the infinity, of the residue when Z2 goes to P, omega of Z2, y of Z2 divided by x of Z2 minus x of Z1. So if you have a holomorphic form, you can write it just in terms of the residue at the alpha nu plus and minus and the infinity plus and minus. So now you can apply it here. And if you do so, you can replace the left-hand side just by the residue at the poles of this part. You can compute it. It's quite a lengthy computation. But it gives you a nice formula, which when you compute it and you sum over h and n, such that 2h minus 2 plus n is equal to k, to m, you get this formula. Plus sum from m1 plus m2 is equal to m minus 1. ds m1 plus over dx, ds m2 plus, minus, is equal to, so this is very reminiscent of d2x over dx2 applied to psi, minus sum over 2h minus 2 plus n is equal to m. So you sum over h and n such that you've got this property. Sum over p, which are poles, residue when z prime goes to p of y of z prime divided by x of z prime minus x of z times dz prime f h n c prime and z for the other one, divided by n minus 1 factorial. Okay. So, yeah, can take 5 more minutes, 10 minutes, yeah. So I skipped all the computations here, but I just recap what's going on. I just write down this equation, which is pretty simple. I can compute this residue thanks to the topological equation formula. This one just because these are simple poles. And I can compute the left-hand side by applying this lemma. And so I can replace it by the residue at the poles of this part. And it gives me this, this formula. And now I am happy in the sense that the left-hand side, you see, it's really like applying h bar squared d2 over dx2 on psi, which is the exponential of a series in S. So I will have term like that and that. So that's what I was looking for. But I've got this right-hand side, which is pretty good for me because you see that I just compute residue at the poles of y dx of basically omega hn. So I can write it in terms of variation of fhn plus 1 with respect to the times. And now it's a good exercise to do it. So you just make the expansion when z prime goes to one of the poles. You expand this part. And you will recognize the variational formula I did write down before. And it gives you that psi plus or minus of x h bar is solution to a differential equation. So I've got this h bar square d2 over dx square, which gives me these terms here. But I've got some corrections. So I have the sum over k belonging to the set k infinity I introduced before. U infinity k of x times d over dt infinity k. You recover what we had found for the equation of the spectral curve, where we were acting on omega 0, 0, minus h bar square sum over k in k nu lambda, u nu k of x d over dt nu k, and u sum over nu going from 1 to n, minus h of x. And all this acting on psi, plus or minus of x h bar is vanishing. So this part gives me this differential operator acting on psi. And there's object here, they just follow from there, where h of x is basically the action of this operator here on the logarithm of the perturbative partition function. Plus h bar square, sum over nu from 1 to n, sum over k in k nu, u nu k of x, d over dt nu k. So here it's just repeating this operator, acting on log of z, which I introduced before. But you just remove the leading order in h bar. And you add y square of x, which we did compute before. So,
that's a power series in h bar.
Sorry?
That's a power series in h bar.
Which one?
H of x.
H of x, yeah. Yeah. So you see, it replaces kind of, I mean, the leading order is basically the H0 we had before, and now we've got all the corrections here. But the differential operator we had before acting on omega 0, 0, so the leading order of log z, is actually acting on psi as well. So it's not a differential equation, it's not a quantum curve that we are looking for. It would be if we would remove this part. But it's a partial differential equation. And what Olivier will show in the next lecture is that this part we can remove it, but the price to pay is that we will have to change this psi quite a lot. Before I finish, yeah. So there were questions about the integration path for the definition of psi before. So I said that you had issue around the poles and so on. Now we can wonder what happens if we go around A or B cycles. So we've got some monodromies for psi of xh bar. And so if we take x going along the cycle AI, it's pretty easy to make the computation, so psi plus minus. It's exponential plus or minus 2 pi I. Yeah, let's go along Hj, epsilon j over h bar, psi plus minus of x h bar. So what is the proof for that? Psi is built out of the omega hn. There is one property of the omega hn, which is that the period of the omega hn. Okay, this one?
So essentially, redo the whole
Exponential plus or minus 2 pi I epsilon j divided by h bar. So you just have a shift of psi plus minus by some exponential factor. Okay? And this follows from the fact that if you take the integral along ai of omega h n plus 1 of z1 up to the n, it is vanishing, so we've seen it for omega 0 too, but it is vanishing unless h equals to 0 and n is equal to 0, in which case it's equal to epsilon I. So not much changes in the definition of psi when you go around a period. You've got this big series, see it's exponential of a big sum, but in the sum there is only one term, which will change. And it gives you this part. It's the one which is the in factor of h bar minus 1. If you go along B cycles, it's a bit more tricky. Yeah. Because all of them will change. We don't have this nice property. But because we have a nice variational formula, exactly as before, for the times, but now for the filling fraction, the B period of omega hn plus 1 is equal to d over d epsilon j of omega hn. Because of that, you can see that formally, when x goes along a B cycle, you will have that psi. It's a bit more complicated. Psi of x h bar seen as a function of epsilon, so epsilon 1 up to epsilon j, changes to z of h bar epsilon plus plus or minus h bar ei. So you consider z where you shift epsilon I by epsilon j by h bar.
Excuse me, what is epsilon?
Epsilon is the filling fraction. So epsilon,
Yes, okay.
it's the vector built out of the A period. So if you shift x, if you go around the B cycle, you consider the ratio of the shifted z where you shift epsilon j by h bar times the same thing, psi of x h bar, and you take epsilon goes to epsilon plus or minus h bar ej. So basically, A period is just multiplication by a factor. B period, if I would work with z times psi, it's exponential of the same thing where you replace epsilon j by d over d epsilon j. So it's a shift operator. So it shows you already that there is no hope that this psi is a good solution to a differential equation because you don't have good monodromy property as a function of x. And this is what Olivier will solve now in the next lecture. And by doing so, he will be able to get rid of this part. So I will stop here. Okay. Is it better? All right. So there are two issues at the moment. So the first one is the monodromy issue here, because the perturbative wave functions that we have here, they don't have good monodromies. So this is the first problem that I will deal with now. And the second one is that at the moment, we only have some PDEs here because of time derivative terms. So this we'll have to remove at some point and transform them into x derivatives. So this will be the second step of my lecture. And when all this is done, we will get to a quantum curve as before. So first is the monodromy issue. So if we look at what is happening is on the B cycle, we have a shift here of the wave function. And when you have these kind of problems, there is a natural way to cure it. It's just if you have a discrete shift in a function and you want to remove it, you just sum over it. And this is exactly what we are going to do here. Is just we'll just sum discretely over these filling fractions. And by doing so, this will remove the shift. But we have to be careful here because it's not only this shift appearing, you also have this factor here. So if you think about it, it's not so hard to guess how to take it into account. You will have to sum over the filling fractions and use a prefactor that will be chosen to remove this kind of things. And this, we arrive to the definition of the non-perturbative wave functions, which are the following. So I'll start with the partition function. So, I don't know. So I'll just, so Z non-perturbative. So it will depend on, of course, h bar, spectral times, filling fraction, and some additional vector rho here. And this is defined as a discrete Fourier transform. So when I say you sum over, you discretely sum over, this corresponds to a Fourier transform, and just 2 high pi over h bar, and just sum over j equal 1 j of kg o, and times, so the z introduced here, h bar t's. Okay. So here k is a vector here, and you just, so this is a discrete Fourier transform. So of course, if the genius is 0, you don't have to do this because the sum is empty, and you don't have monodromy issue because you don't have cycles. So this is the real new thing on non-vanishing curve, is that you have to introduce this kind of Fourier transform, and you do the same for the non-perturbative wave function. For the wave function, but you have to take care of the z factor here, so you have to do it in a way that your final monodromy will be what you expect. Depends t epsilon rho. And this is defined, so you've got your 1 over z. So the perturbative one depends on h, t, rho. Sorry, over here. So this is the one which is here, so it's non-perturbative one. And again, a sum discrete transform 2I pi over h bar sum j, kj, j, and then here you have so the perturbative j, here h bar t. So same story, it's a discrete Fourier transform, but so this would be without this factor z here. And if you want to get good monodromies and remove this ratio here, then you have to introduce this z and this z non-perturbative. And when you do this, formally, so this is all formal in h bar because at this time, all we do is purely formal. And when you do this, well, it's straightforward computation. To get that this time, so the capital psi plus or minus h. They have good monodromies in the following sense.
Excuse me, I missed what are the hat. Oh, are those vectors or not hats, right?
Hats.
This the.
It's all
vector,
vectors.
yeah.
Okay.
And okay, so you take this. Okay, yeah, that's fine.
So it's a sum of a discrete sum, but in dimension j. And so what do I mean by good monodromies? Well, it's exactly what you would like. So so on the A cycle, nothing happens. And on the B cycle, it's so there is when you go around, you don't have this factor anymore. You don't have the shift. And what you get instead is just an exponential term. So minus plus 2 I pi j over h bar. Okay. Maybe I should say this depends on rho. Okay. And this is nice because it's only exponential factor that do not depend on x. I mean, it's quite trivial. And especially in the following, we will have products between psi plus and psi minus. And when you do this, you don't get any monodromies because the sign compensates. So this will be quantities that will have no monodromies. And the purpose of that is that if you have no monodromy and no essential singularity, you will get rational function of x. This is why we want this property. Okay? So this seems quite simple, but there is a big price to pay. That if you look at the h bar dependence of the wave function is much more complicated. As before, than before. So what we want is even, so this is the informal presentation. What we will do in the end is, so remember that this kind of function, it was just some exponential of sum over k equal -1.
Excuse me, can I ask what you mean by much more complicated? So it's not
Yes.
a series expansion, or do you have more?
Yeah, I'll just explain now. Okay. So this was, so here, SQX. So your perturbative wave function, it was basically what is known in the literature as WKB solution, which is just, if you take the log, it's a formal power series starting at h bar to the power of -1, but it's basically a power series. Now, when you introduce this kind of Fourier transform, what you do is introduce a dependence in h bar in the exponential factor here. And in the end, what we will obtain will just exchange. So what we have is the sum. So if you look at the formula, we have a sum here, and then we'll have a sum over k equal -1 to infinity. So, and we'll just exchange that. Okay. So at the formal level, you can always do it. Of course, if you want to put some analysis behind it, that will be a non-trivial step. And when you do this, what you obtain is h bar trans-series. Okay. It's a trans-series of h bar. So in the following sense, that, well, let's write it for the partition function. It's the same. So this should be understood as some.
Excuse me, are you now using k for two different sums?
Yeah. So one is a vector and the other is not. So.
Okay. Sure.
But, so wait, okay. Just, it was the notation used by Nicola before. So maybe I should put an M here. So at some point you want this sum to be on the left, because, and so you have to switch it with this one in the exponential. And when you do this, you can resum this summation over k, and what you get here are some kind of derivative Riemann theta functions. So I'm not going to enter into detail, but this gives you some transmonomials, and you can expand in this transmonomial. And when you write equalities between two quantities in this space, this means that all coefficients in the transmonomial should be equal. This is the way we will write down quantities. It's just order by order in this grading, quantity coefficients are the same. So this is completely formal. There's no analysis behind it. This is a
the challenging question of what sense can we give analytically to this kind of solution, but this is not done here. Yes. Yes. This would be, well, I mean, it could be written down, but it's quite lengthy.
I just have the first word. I can't read it.
Okay, it's and evaluated at, maybe I should, because the edge dependent. That's which is something over h bar. Okay, so the h bar dependence only comes from the evaluation point here. This is what gives you the transmonomial. Okay, but this is just, I won't use it much, but all equalities that we will write down has to be understood as equalities between h bar trans series. Now, before it was equalities between WKB series, and now this has to be understood as equalities between trans series. Okay, this is just technical aspect. So what happens when you do this kind of discrete Fourier transform? If you look at the equation that you had before, but almost nothing, because this is linear. It's a linear equation. And this kind of transformation goes well into linear quantities. So you just write down term by term and look at what's happening. And basically, almost nothing. The only change that you have is, of course, non-perturbative quantities turns into non-perturbative quantities here. And the only difference is this part here. This also turns into non-perturbative quantities. And this is, I mean, straightforward. Discrete Fourier transform is linear, is compatible with linear differential equations, so it's just go through term by term. It's nothing to do. Okay, so maybe I should develop a little about this partial differential equation. So if you think about quantization, there are good terms and some more unexpected terms in this equation. So these ones and this one. So the blue term would correspond to a naive quantization of the initial spectral curve. So naive in the sense that you would just replace y by h bar d over dx. And this would give you these terms here. So this is what happens, for example, in the Airy case. You just have these terms. More surprising, more unexpected are these terms here. So these terms, so red terms. Okay. These are h bar corrections because they depend on h bar with a h squared factor here. But the good point is that the dependence in x is rational with pole in the initial poles here. Because dependence in x is only contained in the u's here. And if you look at the formula that Nicolas gave before, it's just so for this one polynomial in x, and this one are just 1 over x minus lambda mu to some powers. So this is rational dependent that we like. It's exactly the same as the one that we have initially. And finally, you have these terms here. So black terms. So these are PDE terms. So they involve derivative of the wave function relatively to the spectral times. And this is what makes, so far, this equation a PDE and not an ODE that we would like. So this is the second step is how can we remove them in order to obtain an ODE. Okay. And to do this, well, there are several steps. So I do not need. So the question for now is
am I reading right that the first two lines of H are the same as the black terms?
it's all right.
In H over there, the first two lines on the lower half? Yeah. Those two terms are the same.
No. This is important. So this one, so the U's are the same, okay? But these derivatives apply to psi. Here, the derivative applies to log z. So this does not depend on x, okay? Z here does not have any x dependence. So this term is, the dependence in x is only there and there. Okay. And this is not the case here because psi depend on x, so you have real dependence when you apply this. So of course, these derivatives apply to log z. It's unknown a priori. I mean, you can compute it from the spectral curve, but this is coefficients. Okay. But they do not depend on x. So, to do this, we need to introduce a few quantities. So basically, what I want to do is introduce the following transformation. I want to write it as, so I don't want to change the first line. Okay. So this is what I want to do is change a derivative relatively to TPK to something which is a combination between psi plus and a derivative relatively to x. And to do this, I have to introduce some notation in order to define Q and RPK. This could be done in the following. So first, you introduce some scans, W of x. I have to put the sign. And you also need to do Wronskian relatively to pk. Okay, so these are Wronskian, and from these you can easily check that the RPK appearing in the matrix here, it's just the ratio of your Wronskian. And Q is just, so it's a little more complicated. So there are two formulas that I will use, depending. So it uses mixed products. And this, okay, for now, I'll just write it down here. Okay, good. No. No, definitely not. This is just a notation that I will use. So, I mean, this is quite trivial to do it. For example, in this one, if you look at the time Wronskian, and so it involves this kind of derivatives. And when you do, when you write down what should be coefficient here, so you see this should be psi plus times q plus r times the x derivative. And when you replace q and r by this formula, some terms cancel, and you just get only this term here. The only one survives, and you can do the same for the other one. So it's just straightforward computation. You just have to.
Sorry, what's the h-bar dependence of R and Q? Are they trans-series as well, or?
Yes, everything are h-bar translate. So I did not write the h-bar dependence, but of course everything depends on h-bar.
Okay, thanks.
Okay.
And this is the answer to that question, or is it just the beginning?
It's just, I mean, I want to rewrite these terms as terms involving psi plus and minus and derivative of psi plus and minus only relatively to x. And to do this, you know, I just take one term here, so the time derivative of psi here, and this formula makes it changing this term. I can express it as a combination of psi plus and the derivative of psi minus. But the price to pay is that I will have some coefficients. And for now, they just are written here. Okay? And you see in the formula, what you have is not only one time derivative, but you have this combination. And in order to write down the quantum curve after that, I will also sum these and define. So R of x, which is just a sum. Pk of x times Pk of x and q. So it's defined so that all this black terms here.
What is tau?
Tau.
You have tau.
Where?
It's a badly written x.
Yeah, probably.
That's x also.
It's x everywhere, normally. I don't see a tau from, but. So this is all done so that these terms here is just, so the first one, so u, x, so if you write down what is here, this should be just q.
Excuse me. So
Plus.
essentially what you're doing, you are saying for every t, we have a kind of quantum Wronskian. I suppose you're missing
Yes,
an
this
h
one.
bar there. Yeah.
Okay,
And,
yes, probably.
and the idea is that you would like to express this Wronskian in t as a Wronskian in x.
Yes.
And to do that, you decide that you do some matrix
Yes, but, well, I
formula.
mean,
But this is kind of miracle in the sense, I mean...
well, it's not a miracle. It's just a definition of Q and R. So far, this could be very complicated function.
But no, I think it's a miracle because, sorry, it's a miracle because you have some big PDE in which I have lots and lots of T's which are mixed. And now you're saying they're separable.
I'm not saying that.
And that pen is not working anymore.
Okay.
Yes, I understand chain
This
rules.
is just...
No, listen. Yes, my point is not chain rule. My point is that you are doing it for every T, P, K separately.
Yes.
And in your equation, they are all mixed together. That's
Yes.
why I say it's a miracle.
No. It's just a definition. There's no statement yet. I mean, you can always say a time derivative is an x derivative times this quantity, okay? But this has very bad properties. But you can always write it and say, okay, I call it R or Q. And this is just notations here. The main point is that at the end of the day, we'll have to prove that these quantities are rational functions with good poles property and so on. This is the hard part, okay? But so far, it's just a rewriting of all quantities that I will need in order to write down this equation as an ODE at some point, okay? So with all this introduced, what you have here is just Q of x, which is just Q times psi, and you just also have R times the derivative here, and if I have the correct factor of h bar, this should be, okay, just this, okay? So this is just basically notations, okay? It's just, I do it for one time here, and then I have to sum with these u prefactors, and this is why I define R and Q, and at the end of the day, only this quantity will appear in the quantum curves, but I will need these intermediate quantities in order to prove that these have rational function with good properties, and automatically this will follow for this one, okay? Right. So at this moment, what I have is now an ODE. Which is, so that's h bar squared. Yes?
does your Q have anything to do with the Q from the y square equals Q of x? Or is it a different Q?
The Q from?
The Q that you define here?
Yes.
Started from like just a curve being
no,
y squared
no,
equals
no,
Q of
no,
x. Okay,
sorry.
it's a different Q.
Q, I'm going to put a Q tilde. Okay, sorry about that. So just to have a good one, so it should be, and so the H here, so this whole line to okay, so Q tilde here, and when I write that, it should be an H factor. Okay. Okay, and it's minus sign. Okay. So this is the ODE that we have, but okay, as I mentioned, this is just notation. So far, the ODE has no interesting information. If we do not have properties for so R and Q tilde. Okay. Well, this is so what kind of properties we want is to have a, so this is a quantum curve. In some sense, it's an ODE that is linear of order 2. And if we want it to be a good quantization of the initial spectral curve, we need it to have exactly the same pole structure. Okay? This is what we expect from a quantization to be a good quantization. If you have something which gives you an ODE with logarithmic terms and even not rational function, this is definitely not a good way to quantize your initial spectral curve. So this is the last step that we need to prove, is that R and Q tilde have good properties, and the properties that we want to get so it remains so the first step is that we have rational function. Second step is, if we can show that these are rational functions, we need to control the location of the poles. So what we want is prove that R, Q tilde have poles only in P. And even more, so P is so infinity and lambda 1 lambda n. So the same as the initial spectral curve and nothing else. And the third step is that we need to control the order of the pole. Are the same as the initial spectral curve. Okay, so if you have, for example, at infinity a pole of degree 4, then you need to have quantities that have a pole at infinity, but not of order 7. Okay, let's say you need to have 4 or less, but nothing. So this is what remains, and this is the hard part. Okay, so far it was just rewriting with new notation, and you see this is not, I mean, steps that are really obvious from the definition. But we have all the ingredients now to prove this. So first, rational function, and this is where the non-perturbative contribution really goes into play at this level. Okay. So step 1. How can we prove that we have rational functions? Well, as I mentioned before, the key argument is that if we have function with no monodromies and no essential singularities, automatically it's a rational function. And this is, we've done everything so that this will be true. And so how do we, so step 1. So you start with the Vronskyans, W and WTK. These are rational functions. So they have no monodromy. And no essential singularities. This makes them rational functions. Okay, and I stress here that the first condition here is only true if you have the non-perturbative correction. If you don't have them, psi function have bad monodromies, and when you do these products, you still get monodromies. With the good monodromy, this one comes with a plus, minus sign, and this one comes with a plus sign. It does not depend on x, so you just get one in the end when you do the products. Okay, so this is why you need non-perturbative corrections. When you have this for the Vronskyans, and this is also the same for the time Vronskyans, because the monodromies, they do not depend on the spectral time. So there's nothing to do. When you have this, then automatically you see you get then that RPK is a rational function because it's a ratio here. And for this one, it's a little more complicated. Okay. For Q's, it's a little more complicated. You need to rewrite it a little. Well, the argument could directly follows from the same as the Vronsky. So here it's not technically a Vronsky, but it's a product of something in psi plus times something psi minus. So there is no monodromy here. And so the argument would be exactly the same. Otherwise, there is an alternative formula that we can do in exercise is to show that you can rewrite it only using the Vronsky. And in any case, so there is a 1 with W of x, and there is a UPK. And you have a derivative TPK minus okay. So this gives you automatically that it's also a rational function. Okay. So this is something important. And when you have the result for RPKs and QPKs,
Sorry,
remember that the
it
use...
seems now you're using P and K both as arguments of Q and as summation indices?
Sorry.
In the last formula you wrote?
Okay, sorry. Yes. So this one is the same. What? There's no summation, sorry. It would be Q tilde, which would be the sum here. Sorry. Okay. Okay, and when you have this for these functions, then you automatically have the result also for R and Q tilde, because the U function here is a rational function that was defined by Nicola earlier. So you get in the end, yes. So the first step is done. Okay, and again, I stress the monodromy argument requires the non-perturbative correction. Otherwise, it doesn't work. So step 2. Okay, step 2 is the hard one. Location of the poles. Okay. It was just, I can shift it over here. It was derivative. To sign, just gonna stay. Sorry. So this is, if I write it this way, there is a minus. Okay, step 2, location of the poles. Well, if you look at, by definition, so your non-perturbative wave function, they are constructed by topological recursion. So this is what Nicola did this morning. So you have the discrete Fourier transform, but this is not an issue. And you have the perturbative wave function. And the perturbative wave function, they are constructed by topological recursion, which means that you have possible poles at critical values. So x of r. So the image by the x function of the ramification points. And this, you want to exclude these points. So the critical values are, of course, in the initial set. So poles in P is what we want, but the other one is not what we want. Okay, so we have to find a way to exclude the existence of poles at critical values. So the wave function will have these singularities, but what we want to prove is that R and Q tilde, they don't have poles at critical values. And this is the real difficult part here, because by definition, they should have, okay? So you have to find a way to prove that. Okay, this I can move. So one of the main results is to exclude and show And this is the only result that I will not prove in the lecture, because it will take approximately 4 or 5 hours. So we don't want to do this. So maybe I'll just mention how this is done. Well, this is not our idea, but so idea of the proof. So you write down, this is why it's technical, because you have 3 derivatives. So you write down that this equality is true, so the second derivative in x times, well, you can just exchange time derivative and x derivative, and you write it for any transmonomial. Okay. Okay. And this gives you a series of equations. And at leading order, you first obtain something. At leading order in H bar, you obtain a first equation. And then this will prove that the leading order is regular at the critical point. And then to do the next order, you have to make a very technical induction, order by order, and prove that, okay, it goes through the induction. And this is a step which is very, very, very long to write down, and that I will not do today. My main idea is that it's all something of the H bar grading, is when you take a derivative relatively to a time, you decrease the order in the H bar gradient in your transmonomial by 1. And this is how you do the induction here. If you do an x derivative, this is not true. This preserves the grading. There's no decrease. And so you have to be careful when you do this. And when you do it, you can inductively prove that all quantities, all coefficients in the H bar transmonomial are regular at a critical point by induction. But this is like a very long induction proof. Okay? Okay. So I'd like to finish this part. So if you assume this, then the rest is quite easy. So if you have it for RPK and QPK, then it's pretty obvious to get the rest. Okay. So then so the next step is to rewrite so the coefficient R in another way. So this is just, so remember, this is the term which is in front of the first derivative. So this, when you have a second order ODE, this is always possible to, I mean, this is equality. The term in front of the first derivative is always, can always be written as these quantities. Otherwise, you just do the computation. Okay. So this gives you that, so you have, I mean, you assume the result for RPK and QPK. This gives you the results for R and Q tilde, because it's just a sum of these quantities. And with this one, you get that the Wronskian is in X is regular at the critical values, because by contradiction, if there was a singularity, this would create a singularity for this one. And this is not possible because these guys are regular, so R is also regular. So this is okay, and the last quantities are for Q's, and so you need the Wronskians in time. Okay, and this is also true. And finally, you use this formula to get that. Okay. Because otherwise this is the same. So this is regular. Everything is regular here. So if this had a pole, then this would create a pole for Q here, and this is in contradiction with the result here. So basically, when you have this, all other quantities have the same pole structure. You just need to be, just look at the argument here. But again, this is the hard part that I have to assume today because I would not have time to do it. Okay, so so far we have step 1 and step 2. And this afternoon I will go on step 3, and then I'll go on linearize the system and do things like that. Okay?
Thank you very much.